Hello, my presentation is about sleep spindles and their effect on memory. So, have you ever tried to remember a name, a fact, or where you put your keys and your mind just goes blank? Yet at the same time, you can recall a random moment from years ago perfectly. Why do some memories stick while others are completely forgotten? One reason could be how well you slept last night. During sleep, your body is not only resting, but also going through the memories of the day, deciding which memories to keep and which ones to discard. And deep in that process are tiny bursts of brain activity called sleep spindles. Sleep spindles were first observed 80 years ago in pioneering electroencephalographic studies on sleeping humans. Sleep spindles are short bursts of oscillatory brain activity that typically last between zero point 0.5 to 2 seconds and occur at a frequency of approximately 11 to 16 hertz, most commonly 12 to 14 hertz. They primarily appear at the onset of non-REM sleep, stage N2, when consciousness fades, while being completely absent during N1 and REM sleep. The active systems consolidation theory suggests that during sleep, particularly during slow wave sleep, the brain activity processes and consolidates newly acquired memories. This involves the reactivation of memory traces that were formed during wakefulness, allowing them to be redistributed to more stable neural networks in the cortex. This process is essential for transforming fragile short-term memories into more durable long-term representations. This implies the existence of a carrier mechanism that specifically routes these memory traces through mechanisms involving synaptic plasticity. Now, sleep spindles are proposed as prime candidates in this process because they promote synaptic plasticity, they change themselves upon learning, and they are time locked to hippocampal ripples and slow oscillations. Moreover, the refractoriness and their clustering on the infraslow time scale define time windows during which various processes relevant for synaptic plasticity and for the reactivation of memory traces can be sequentially executed, while also being protected from sensory interference. Sleep spindles are also associated with rhythmic synchronized neuronal activity between pre and postsynaptic neurons and provoke activation of calcium ions dependent signaling pathway. Such events favor the induction of associative forms of long-term synaptic plasticity. Spindle-like rhythmic neuronal activity can thus trigger several forms of long-term plasticity. The theory of active systems consolidation proposes that a triple time locking of sleep-related rhythms between the cortex, thalamus, and hippocampus provides a temporal window and optimal neuronal conditions for memory trace consolidation. Reactivation of memory traces is thought to depend on hippocampal ripples that, when coinciding with the occurrence of slow oscillation sleep spindle events, enable consolidation. Supportive evidence comes from human and rodent studies, during both of which a higher number of coordinated discrete hippocampal ripple and prefrontal spindle events coincided with the slow oscillations. Now, word pair or word image association tasks have been used most frequently to correlate sleep spindles with overnight recall performance. After overnight sleep or a nap, they are asked the next morning or a few days later to recall the second word once they're presented with the first word or image. One aspect that emerges from these studies is that intense learning with 100 word pairs leads to increases in diverse measures of spindle activity of young adults in the initial periods of N2 non-REM sleep in the majority of these studies. An interesting alternative to word pair tasks are visual recognition tasks, which produce changes in spindle-related parameters over parietal areas involved in visual functions. Furthermore, closed-loop feedback stimulation of the prefrontal cortex by increasing the number of ripple-coupled slow oscillation spindle events improves spatial memory. Similarly, through optogenetically promoting thalamic synchronization during the active state of slow oscillation, facilitated contextual fear memory in mice. Also, pharmacological boosting of sleep spindle density promoted various declarative forms of memory, and there's also, in addition to declarative memory tasks in humans, correlative evidence for contribution of spindle-related activity to episodic memory details as well. So, in conclusion, sleep spindles timed by slow oscillations and working alongside hippocampal ripples act as the brain's overnight memory engine, transforming fleeting experiences into lasting memories. Thank you guys for listening to my presentation.